We're continuing with section 3.7, examples, applications of the chain rule. So the discussion here is a lot of times you have a function of one variable, and that variable is depending on another variable, and so you're taking the derivative and how everything works. One example, the most important examples are actually that one variable is changing with respect to time, the other variable is changing with respect to time, even though you don't see it as in a formula, but they're implicitly there, and you have to basically calculate it, the rate of change of one variable and with respect to the other variable. And so how does this work? Let's do the example. As air is pumped into a balloon, the volume and the radius increases. Both volume V and radius R are functions of time. The volume formula for a sphere also expresses the volume as a function of radius. This one we know from grade school. V equal to 4 pi third R cubed, and now we write it as V of R because what is the variable on the right side? R. 4 pi third, by the way, remember it's a constant, right? Constant coefficient. And so we write it as V of R, but we sort of know that V is a function of T and R is a function of T as well. So since radius is a function of R of T, of time T, the dependence of volume on time can be expressed as a composite function. What's a composite function? V of R of T equal to 4 pi third of R of T to power 3. See, we know that R is a function of time, and so we can replace it there. Now, what you see on the left-hand side is a function of T, even though we don't know exactly how to solve it, but we know R is a function of T, and 4 pi third is also 4 pi third R of T to power 3 also contains as a function of, it's an expression of T basically. Implicitly. So now the next question is, so we're always interested in balloon, and we sometimes know the rate of air going in the balloon. I would be interested in knowing how radius is growing, and I may know that how radius is growing. I can figure out what amount of air is blown into the balloon, what rate of air being blown into the balloon, and it's basically partly we're interested because it may pop, partly we're interested to look at the efficiency and etc. And so the question this time though, we're asking at t equal to 1 minute, the radius is 3 inches and growing at a rate of 2 inches per minute. How fast is the volume of the balloon growing? So this time around, I know the radius, and also I know one more piece of information. I know the rate of change, the instantaneous rate of change in radius. So I know the radius, which is 3, and that's R. And I also know 2 inches per minute. It's a rate of, and it's growing, means increasing. So dr dt I know is equal to 2 inches. And so that's the first thing that we know. Now, how do I relate? What is the question asking? The question is asking for how fast is the volume. How fast and volume means the rate of change for volume. That's basically dV dt. So that's what question is interested in, right? And I have to connect dv dt somehow to dr dt and r inches. And again, I may not see t at all because really r is a function of t, but I can quite explicitly tell you what function. But I have all the tools to connect the values at that instance that we're talking about. That instance is time t equal to 1. It may not even use that t equal to 1. Why? Again, because we don't have the basically we don't have the in the r as a function of time, and we don't have that explicitly. So that's important to know. So we start with, since we're relating the dv dt and dr dt and all of those together, it looks like a chain rule to me. So how does the chain rule work in here though? Chain rule for this situation, if I'm taking the derivative of v with respect to time, and I have to take the derivative of basically I have to look at over here, and over here I see 4 pi third r of t to power 3. So there is an inside function and there's an outside function here, 4 pi third being a constant coefficient, and I use the chain rule on this part basically. So again, you may be tempted to try to use the chain rule on this function over here, and that would give you dv dt is equal to dv dr times dr dt, right? And so that exactly carries the same meaning as what we're doing over here, by just taking using a chain rule on that function. So they're about the same thing. And so let's do both ways. If I take the derivative of this directly, what do I get? This one prime gives me let's see, d dt gives me 4 pi third, constant coefficient stays, then the outside function is 3, so multiply by 3, and then multiply by r of t to power 1 less, and then multiply by the derivative of inside. Derivative of inside is just dr dt. If I take the derivative of this side, then I have to go back and reinterpret. What is dv dr? Dv dr, here dv dr is 4 pi third times 3 r squared, and then I have to keep the dr dt. So in either side you pretty much arrive at the same value. It's sometimes easier just to take the right hand side and go with it and not be confused, but sometimes having this formula and going back to the exact formula that relates the two variables other than t is the easier way to go. So depends on how you learn better or makes better sense for you. Just go ahead with that. I'm still writing that 3 over here. Next step, I'll simplify it for the denominator. So either way, it gives you the same value. So after simplifying 4 pi third times 3, you end up with 4 pi r of t squared r prime of t. And now it's time to replace the variables. R of t is 3 inches and r prime of t, or dr dt, is 2 inches. And so you replace it and you get 72 pi cubic inches per minute, and that's how fast the volume of the balloon is growing. And I get 2 to the power 2 plus 2 is 6, and I can plug in h prime of 2, and I end up with 2 times 2 plus 1, 5. So this is a little bit different from what we did previously, which if the t was given, I didn't have a function to plug in, but now I have a function to plug it all in. And so let's say that the t is given, and I can find h prime of 2, I can find h of 2, and then I can find the volume of water changing if that is. Let's do another example of the application of the chain rule. Let's say if a spherical tank of radius 4 feet is filled to height of h feet, then the volume V of water in the tank in cubic feet is given by the formula V of h equal to pi times parentheses 4h squared minus h cubed over 3 close the parentheses. So this, by the way, this formula, you have to drive it in calculus 2, but in calculus 1, and we still haven't learned how to do that. But let's say that we know the formula because somebody in calculus 2 has done it for us. So when you have this formula now, you can take the derivative of v with respect to h and have dv dh. What would that be? That would be v prime of h equal to, and so pi is a constant, and so pi is constant coefficient and stays, and inside the parentheses you have 4h squared, which is going to become, after taking derivative, become 8h, and then h cubed over 3 it will be 3h squared over 3, which is h squared. Now let's say in the question that we just did in the previous page, we didn't have any value that connected h to t, any formula that connected h to t. Let's say this time we have a formula. So the tank is regulated by a faucet and a drain, so that the height of h of water at time t in hours is given by h of t equal to t squared plus t. Okay, so if I know h of t is equal to t squared plus t, now I can find the formula for h prime of t. H prime of t is going to be 2t plus 1. Now I have all this information. This is helping me. If somebody, let's say, give me a time, let's say at time 2 hours, then I can connect all this information together. How I can basically write dv dt to be equal to so dv dt is going to be equal to, according to the chain rule, dv dh, and then dh dt, right? And so I can actually, if it says t equal to 2, I can plug in t equal to 2 in here. And I can plug in t equal to 2. But there's no t for this part. And if you go back in here, there's no t for this part. What do? What you do is you go back and you calculate h. Because that's what this function takes. dv dh takes h. And h can be calculated by plugging in 2. So let's go through every step. At t equal to 2 hours, the height of water is h of 2 equal to 6 by plugging in here. If I plug in 2 for t squared plus t is going to be 6. And then the rate of change for h is coming from this formula. It's 2t plus 1. 2 times 2 plus 1, which is 5. And 5 feet per hour, and h of 2 is 6 feet. And so the last thing is, from what we remember of the chain rule, you need to find dv dh at when t is equal to 2, which means h is equal to 6 that instance. So you have to plug in 6 in there and find the v prime of over here. You have to plug in 8 times 6 minus 6 squared. That is 46 minus 36 or 12. So you get 12 pi cubic feet per foot of water height. So this is kind of different, right? It's not per time, because it's the variable that you're taking the derivative respect to is h. So it's going to be per feet, basically. 12 pi cubic feet per feet. And then you can plug in the values. For dv dh, you can plug in 12 pi. And for dh dt, you can plug in 5, and you get 60 pi cubic feet per hour. And that's the rate of change of volume of the water inside the